Hey everyone, so this week's lab is a virtual equilibrium lab, and I think it can be a little confusing without some explanation, so here goes. So in lieu of being able to do these actual labs in person, I at least wanted you to be able to visualize and see equilibrium shifts in reactions where those changes are visually observable. And so I found a great virtual lab online at this website here, and I have the website pulled up over here. So I recommend that you start by reading the background information just about equilibrium. It's all stuff from the chapters and Le Chatelier's principle as well. And then the pre-lab questions I have converted into this document here, so you'll just complete those on the document. And then the virtual experiment itself. So that will be here at this link under experiment. So there are 6 different experiments that it's going to walk you through. And it's basically 6 different chemical reactions where the reaction is provided and then different things are done to manipulate the reaction in order to shift the equilibrium either forward or reverse. And you can see that equilibrium shift because it results in a physical change or a color change. So let's just walk through the first one together. So the first one is this reaction of cobalt. So it's cobalt chloride. I'll click on it here. So we've got cobalt chloride, which is blue, and that's a deep blue solution here. And it's in water. It's an aqueous solution. And that's a cobalt chloride 2- ion. And this would be a cobalt 2 ion, cobalt 2 chloride. And then on the product side, we have this cobalt hydrate, which is a red ion, and free chloride ions, and heat is produced as well. So this would be an example of an exothermic reaction. Heat is produced. Also, it gives us this note here. It says that silver ions react with chloride ions to form silver chloride. So that's going to be relevant when we add silver nitrate. Okay, so first thing we're going to do is add heat. So we'll click on this little flame here, and we see that it goes from this kind of violet maybe to a bluer, even a bluer solution. So it went from being kind of violet, which was like a little bit of a mix of blue and red, to being really blue. So we'll write in A what our observation was, that it went from violet, like a purple, to a deep blue. And then in B, under heat, we're going to write why we think that happened. So we can see that it went more towards the reactant side. It got bluer. All right, whereas when it was at equilibrium, it was kind of a violet. There was a mixture of blue and red colors. But it shifted towards this blue side. And it did that because this is an exothermic reaction. And when we add heat, since heat is like a product in an exothermic reaction, when we add heat, we shift the reaction the other direction. So we're going to shift it towards the reactants. That's why it became more blue. Now we're going to do the opposite. We're going to cool the reaction. We're going to add some ice cubes here. And we'd expect to see the opposite, right? We expect it to shift the other way and be more red. So let's see. And that is, in fact, the case. It goes from violet to a pinkish color when we do that. So we would say it goes from violet to pink, and it does that because when you cool the reaction, it's like you are removing heat. And removing heat as a product is going to shift the reaction towards the product side, according to Le Chatelier's. Now we're going to add water. All right. If we add water, we see that it gets pink. Okay, so we look at the equation here, and water is a reactant. And if we add more water, we're going to shift it towards the product side, which should make it turn more red. And that is, in fact, what happened. And add potassium chloride. So here's the potassium chloride. We're going to add this. And that turns it more blue. It went from violet to blue. So that's what we'd write in part A for our observation. And why did it do that? Well, the potassium chloride, when you add it, it's going to dissociate in solution to potassium ions and chloride ions, right? Well, chloride ions are part of this equation here. They are on the product side. So by adding potassium chloride, what we've done is we've added more product, which is then going to shift it towards reactants. That's why it appears more blue. And then let's just do a prediction before we do the silver nitrate. So silver nitrate reacts with chloride ions to form a precipitate. So what that means is it's going to pull these chloride ions out of solution. It's going to remove them by forming a precipitate. So there will be less of these chloride ions in solution. So if we're removing a product, we expect it to shift to the right and turn red. So let's see if that happens, and it does. And if you look closely, you can also see some white precipitate, which is the silver chloride precipitating out in solution. So it's almost as good as us doing it ourselves. We don't make a mess, and we don't have to use any toxic chemicals. Cobalt's a heavy metal that has to be disposed of safely. So you'll do that for each of these reactions. So the next one is the ammonium system, and then there's an iron thiocyanate system. So there's 6 different systems that you'll go through, and you'll manipulate it using those little pictures, and you'll write your observations and then why you saw that shift according to Le Chatelier's principle. So the part A is just your observation, what was the color change or the visual change, and then B is what you think was actually happening from a chemical standpoint. And I have some examples here, and we just walked through that whole first one together. So try the rest of them. If you have questions, let me know. Make sure you take note of my little notes here. So like potassium thiocyanate, it forms these different ions in solution. That's what these salts basically are being added for. You can never add ions alone. Ions always have to be added in solution as a salt dissolved in it. Other things to note in the ammonium system, the pink color, it doesn't say in this equation here, but that hydroxide ion, the OH minus, causes a color change in a pH indicator, so it turns pink when there's a lot of OH minus. Most of these, the color is indicated in the reaction. And I think those are the only notes I wanted to make. And then there's some post-lab questions for you as well, just asking, again, further questions about Le Chatelier and equilibrium shifts. So hopefully this one's kind of fun to look at, and let me know if you have questions.